This is exam 3 for Physics 102 in Spring 21. So first we have this RC circuit, a resistor capacitor circuit. I want to know, A, how long does it take to charge this circuit? In order to find that out, we first have to calculate the time constant, tau. That's equal to R times C. That's 5 mega ohms times 2 microfarads. I can convert these to SI units, though you'll see that it's not relevant, or it's not necessary, because the mega and the micro cancel out. And that gives me a time constant of 10 seconds. Now that's not the time to fully charge or discharge the capacitor, but it is a characteristic time. To fully discharge the capacitor or to charge it, we take 10 times that time constant, which is going to be 10 times 10 or 100 seconds. Now the second part of this is how long does it take for the capacitor to reach a charge of 10 microcoulombs. So look at the equation for a charging discharging capacitor. Let's see, I'm looking right here. So I have the charge of a charging capacitor is equal to that. That's a exponential growth function. So I have Q is equal to the total charge times 1 minus e to the minus t over, I'm going to put tau here. Tau is RC, since I've already calculated that. So I'm looking for t here. I'm going to solve this for t. So divide both sides by q. I will subtract 1 from both sides, and that gives me negative e to the minus t over tau. Then I can take the negative of both sides, and then I take the natural log of both sides. At this point, I'll go ahead and put in some numbers. Q is 10 microcoulombs, so that's 10 microcoulombs. Big Q is the charge on the capacitor. I have 2 microfarads and 10 volts, so that's equal to C times V, 2 microfarads, 10 volts. That's equal to 20 microcoulombs. So that's divided by 20 microcoulombs minus 1 is equal to e to the minus t divided by 10. So this is the natural log of a half minus 1 is negative a half of positive 1/2. And that's equal, if I take the natural log of this side as well, it gets rid of that. That's minus t over 10. Let's see, the natural log of a half is negative 0.69. So t then is equal to 6.9 seconds. So that's the answer, 10 seconds and 6.9 seconds. Charge particle enters a 2 Tesla magnetic field. As shown, the particle has a speed of 4 meters per second. What direction does the particle initially travel? So we're going to use our right-hand rule for that. So we're going to let our index finger go in the direction of V. We'll let our middle finger go in the direction of B, and then our thumb give the direction of F. So this is a positive particle, so I would use the answer that I get from the right-hand rule. I have my thumb pointing up. That means that the force is going to be up. So for A, the answer is up or positive y direction. What is the mass-to-charge ratio of this particle? So this is a mass spectrometer. I'm going to look at my cyclotron equation. R is equal to mv over qb. Just want to remind you that this comes about from this. This is the derivation for this, that the magnetic force is a centripetal force. So one of my v's cancels there, and then I can solve this mv over qb to find r. And I'm looking here for the mass charge ratio. So M over Q, which is what I'm looking for, is equal to RB over V. Okay, I'll have to give you the radius, but let's see. Let me pause here for just a second. So on the exam, I'll give you the radius, of course, and I'm going to give that as 3.0 meters. So this is going to be 3.0 meters times the magnetic field, which is 2 Tesla, divided by the velocity, which is 4 meters per second. That's 6 divided by 4, or 1.5 kilograms to coulombs. So that's the answer. And again, I will give you that radius in the problem. Okay, here first I want you to draw the rays as it goes from one index of refraction to another. So let's look at N1 and N2. N1 is traveling fast, and here is traveling slower. So if I think about my wave fronts coming here, it's going to slow down here, and that means it's going to bend towards the normal, like that. And here is traveling slow and then faster, right here. So if I think of my wave fronts coming here, they're going to speed up at this side, and they're going to bend away from the normal. So those are the light rays that I want to see, bending towards the normal and then bending away from the normal. That's A. And then what is the angle of the light ray from the perpendicular line as it emerges from the third medium? So I want to know as it goes, actually, from faster, rather slow in this medium to faster in this medium. I want to know what is this angle, and it's going to bend towards the normal in that case. And I want to know what is this angle theta. So that angle theta I can find by N1 sine theta 1 is equal to, hold on. Okay, I'm going to change this just a bit up. I'm actually going to change the wording of this problem to ask for this angle, which I'm going to call theta 3. So I'll ask for the light ray as it emerges into, or as it goes into the third medium, that angle theta 3. I'll reword that. Anyway, so N1 sine theta 1 is equal to N3 sine theta 3. Remember, I can get rid of this second medium, and it works out like this mathematically. I know that N1 sine theta 1 is equal to N2 sine theta 2. And I also know that N2 sine theta 2 is equal to N3 sine theta 3. So these media are linked in this way. And because N1 sine theta 1 is equal to N2 sine theta 2, and N2 sine theta 2 is equal to NC sine theta 3, then I can say that those two are equal. So this is going to be 1.2 sine of 50 is equal to 1.1 sine of theta 3. So theta 3 then is the inverse sine of 1.2 sine of 50 divided by 1.5. And that's 38 degrees. So that's the answer, 38 degrees. That's theta 3. Electron approaches a wire with a current of 2 amps as shown in this figure. Has a velocity of 3 times 10 to the 5th. This is I, this is V, and this is the distance. So I think we call this R in the equation. First I want to know what is the direction and magnitude of the magnetic field at the location of the electron. So if I go back to my equation sheet, I give the magnetic field due to a coil of wire right here, or not, to a long straight wire right here. I can tell right away the coil of wire looks very similar except it has the N. So it's mu naught I over 2 pi R. V is equal to mu naught I over 2 pi r. That's going to be 4 pi times 10 to the um, minus 7, I think. Let me just double check that. So you go over to your equation sheet, you can get that mu naught is right here, yeah. All right, times the current, which is 2 amps, divided by 2 pi, times the distance, which is a 0.25 meters. These pi's cancel. I can cancel that 2, and I'm left with 4 times 10 to the minus 7 divided by a quarter. That's 16 times 10 to the minus 7. That is the magnetic field. Now I also want to know what is the direction of the magnetic field. I'm going to use the third application of my right-hand rule. My thumb goes in the direction of the current, and my fingers wrap around to give the magnetic field. So my thumb goes in the direction of the current, and my fingers go into the page on this side and out of the page on this side. So it's 16 times 10 to the minus 7 Tesla out of page. Or I could put that as in the plus z direction. And now for B, I want to know what is the direction of magnitude of the magnetic force on the electron. So first, I can just calculate the force. That's QVB sine theta. Here, those two are perpendicular to one another, so that's sine of 90, which is equal to 1. And I have an electron that's 1.6 times 10 to the minus 19 coulombs. That's on your equation sheet. The velocity is 3 times 10 to the 5th. And then the magnetic field I found is 16 times 10 to the minus 7 Tesla. So that gives me uh, 7.7 times 10 to the minus 20 newtons. So that's the magnitude of that force. I also want to know the direction of the force. So we're going to use the third application of the first application. So our index goes in the direction of V, our middle goes in the direction of B, and our thumb gives the direction of the force, which is what we want. We also need to recognize that this is an electron. Hopefully you made a note of that, that if I have that electron, it's going to change the direction. I'll come up here. I think about my velocity is to the right. My magnetic field is out of the page on this side, so that means that the force would be down if it were a positive particle, but it's not. It's a negative particle, so my force is up. So you can show that. You can say that it's up, or you could say in the plus y direction. I would probably also take a vector if you draw the vector in that way. Okay, so that's the answers for theirs. There's the magnetic field, there's the direction, and here are the directions for the force. Okay, let's look at the multiple choice. What is the time constant? Oh, we've already done this one, right? So the time constant here, whoops, is all right, let me fix this. The time constant tau is equal to r times c. That is 5 times 2, or 10 seconds. And I already talked about how the micro and the mega cancel out. Capacitor is allowed to fully charge. Which of these represents the voltage versus time for that capacitor? Well, when a capacitor is charging, that is a growth function. And we know the exponential growth function looks like this. Which of these statements about a household circuit is true? The GFCI is used in areas prone to be wet. Yes. Bathroom, kitchens, garages. All devices operate at the same voltage. Yes, they all operate at 120 volts. Third prong measures the incoming current. No, that would be the GFCI does that. And the circuit breaker compares the incoming current to the outgoing current. Okay, no, that's also the GFCI. So only 1 and 2. You have these devices on a circuit. What is the total current through the circuit? So this is what an electrician does when they plan out your house, is they ask, what are the devices that are going to operate on this circuit? And they calculate that total current as P over V. So the heater, for example, would be 1200 watts divided by 120 volts, or 10 amps. The others are 600 divided by 120, or 5 amps, and 120 divided by 120, or 1 amp. So I get 10 plus 5 plus 1, or 16 amps. By the way, your electrician will also plan out your house so that if you turn out, say, one circuit, it doesn't, for example, turn out all the lights in the entire house. So they'll work in zones through your house. You'll see that, oh, the living room is on this circuit, the bathroom is on this circuit, and on and on. Electron travels in the plus y direction through a vacuum in a region of uniform magnetic field that is also directed in the plus y direction. The electron, okay, so the velocity is in this direction and the magnetic field is in that direction. The angle between those is 0, so our F equals QVB sine theta. The sine of 0 degrees is equal to 0. So there's going to be no force acting on it. In fact, if a particle travels parallel to the magnetic field, it doesn't affect it. Electron and proton are both initially moving with the same speed and in the same direction at 90 degrees to the same uniform magnetic field. They experience magnetic forces which are initially what? Okay, so they're traveling orthogonal, same speed, same direction, and the same magnetic field. The magnetic forces, because the electron has a negative E and the proton has a negative E, they will experience magnetic forces that are equal in magnitude but opposite in direction. C and D are referring to they have a different ratio of masses, so that will affect their acceleration, by the way. So they'll be their acceleration would be different, like in this way. Hold on, let me pause for a second. Okay, so E is saying that the forces would be like this, but that's not how the forces would be at all. Okay, a wire carries a current of 1 amp in a direction that makes an angle of 30 degrees with the direction of a magnetic field. So here's my current, and here's my magnetic field at an angle of 30 degrees. I want to know what is the magnetic force. So this is a simple F equal ILB sine theta. You do need to use the theta here, so I have 1 amp. The length of the wire is 5 meters. B is 2 Tesla, and sine of 30. So this is 10 times a half, 5 newtons. Which of these statements is true? The Earth's magnetic north pole is at the geographic south pole. That's where the penguins are. Yes, that's true. They're at the south pole. So yes, that's true. So if you look at the Earth, North America, South America, Europe, Africa, this is Antarctica. That's where the little penguins are. This is the magnetic, or this is the southern geographic pole, but it is the northern magnetic pole. So that's true. Magnetic fields are caused by moving charges. True. Wood is not magnetic. That's true. It's not ferromagnetic. And it does not have any moving charges. Not true. It does have moving charges, but as I look at a piece of wood, the magnetic domains within that wood are all randomly oriented. So it doesn't have a magnetic field. So A is the right answer for number 8. Whoop. This figure shows the path of a charged particle as the direction of the magnetic field that has caused this motion. Okay, so there's a couple steps in here. First of all, my velocity is in this direction and my force is in this direction. So I'll use my first application of the right-hand rule. Let my finger go in the direction of velocity, my thumb in the direction of the force, and then that gives me a magnetic field that is into the page. Oops, however, this is a negative particle, so I'm going to go back and I'll fix that and say that the magnetic field that causes this is out of the page, so B is the right answer. Positively charged particles traveling to the left and experiences an upward force. What is the direction of the magnetic field? So here, this is a really similar one. This is positive. My velocity is to the left. My force, which is going to be my thumb. This is my index finger, and then my middle finger is pointing out of the page. These two wires generate magnetic fields. What is the direction of the resulting magnetic field at point P? So we use our third application of the right-hand rule, my thumb in the direction of the current. My fingers wrap around the direction of the magnetic field. So in this one, my thumb is pointing towards me, and so my magnetic field goes in this direction. That means at point P, my magnetic field is down and in that direction. For the other one, it's into the page. This one is going to go like this. So over here, the magnetic field points down and in that direction. That means that the total magnetic field is going to be at point D. Charged particle travels in a path as shown in this figure. The magnetic field is into the page. It shows the direction of the charge's path. What is the sign of the charge? So I have this particle that is traveling in a circular pattern. I'm just going to take a piece right here. I'm going to imagine this part right here. I'll redraw it over here. I have a velocity that is to the left, and I have a force that is pulling up towards the center of the circle. In fact, that's always going to be the same, the velocity and the force. This is the velocity, this is force. They're perpendicular to one another, and that force is acting as a centripetal force. But I'm dealing with a situation down here. Okay, so now I use my right-hand rule. The velocity is to the left, the force is up. That means I would get this type of motion if this were a positive particle, because when I do this, I figure out that the magnetic field has to be out of the page in order to generate that force. However, the magnetic field I know is into the page, and so that means that this must be a negative particle. Charged particle with a charge magnitude of 3 coulombs and 6 kilograms mass travels at 4 meters per second, as shown in the figure for the previous problem. The magnetic field has a magnitude of 2 Tesla. What is the radius of the charge's path? Okay, this is the mass spectrometer. R is equal to mv over qb. Remember, I get that from the magnetic force, qvb, when the force is perpendicular to the magnetic field, and the velocity, orthogonal, is equal to mv squared over r, and then I solve that for r. And so here I have 6 kilograms, which you're not going to have a charge of 6 kilograms. It's not a physical representation. I just use these numbers because they're easy. 6 times 4 meters per second divided by Q, which is 3 coulombs, and then B, which is 2 Tesla. So this cancels with that, and I'm left with 4 meters. It's going to have a radius of 4 meters. So in this will have a radius of 4 meters. Newton explained light as a particle because of reflection. Huygens explained light as a wave because of refraction. So A is right. Organize these in order of shortest wavelength to longest wavelength. I usually think of light in terms of energy. So I could think of this in terms of highest energy to smallest energy. But we can think of it in wavelength too. Longest wavelength. The longest wavelength that we have is radio. The shortest wavelength, or the highest energy, is gamma. So I'm looking for something that ends in radio and something that begins in gamma. That leaves me either B or C. Ultraviolet light is a higher energy than visible light, or a shorter wavelength, so B is the right answer. A ray of light is incident on a plane mirror as shown. What is the reflected angle theta r off of this second mirror? So if that angle is 40 degrees, this angle is 40 degrees, and that means that this angle is 50 degrees. If that angle is 50 degrees, that means this angle is 40 degrees. Which means that, I'm going to redo this figure a bit, but it means that this angle right here, actually let me redraw this. So I have a light ray that comes in, it reflects off, and it goes off again. Actually, we'll come back in that direction. We'll see they're the same. So if this angle is 40, that means that this angle is 40, this angle then is 90 minus 40 or 50. If this is a right angle, that means that this has to be 40 because these two angles have to add up to 90 plus this third angle will give me 90, which is 180. And then this angle is 90 minus 40 or 50, which means that this angle is also 50. All right, I'll make this figure a little bit better. And 17, which of the following is true? Regarding the indices of refraction, draw my marching band. On this side, it's going to speed up, causing it to go here. So I know that I have a fast velocity here, slow relatively velocity here. That means that I have a big index, small index. So N1 is bigger than N2. Index of refraction is dependent on wavelength, shown in this figure. When white light passes through a prism, which color will be bent or refracted the most? Okay, so this is blue light, and this is red light. The one that will be bent the most is the one with the bigger index of refraction. So blue will be bent more, followed by the spectrum. Roy, you bit backwards. Okay, I'm sorry. All right. What must be the angle theta1 for the ray to go total internal reflection? Let's just make sure that we get total internal reflection. Since we're moving from a big index to a small index, then indeed we do get total internal reflection. In fact, this is like a fiber optic cable where I have a big index, glass or plastic surrounded by air. And then I can solve for what must be the critical angle. So N1 sine theta 1. In fact, I'm going to get rid of this 1 and call this my critical angle. That's what it is equal to N2 sine of 90, which of course is equal to 1. So theta C is the inverse sine of N2 over N1. Or the inverse sine of 1 divided by 1.4, which is 46 degrees. And then the last problem, fiber optics cable. What can you say about the relationship between the indices of refraction for the cladding and the core? Well, we just had this, right? So the core is the higher index, so that means C is the right answer. Okay.